Operational technology enables modern society by delivering critical infrastructure such as electricity and water, managing complex transportation networks, delivering advanced healthcare capabilities, manufacturing our goods, producing and distributing our food and medicines, and regulating our environments. The importance of OT, however, also makes it an attractive target for a number of threat actors: nation-states, hacktivists, organized crime groups, as well as competitors. Disgruntled employees and terrorists have focused attention on OT networks to further their own aims of control, disruption, sabotage, extortion, espionage, and theft. In the following demonstration, a competitor has targeted a pharmaceutical company in order to conduct industrial espionage to obtain details of a newly developed drug and to lower efficiency by causing changes to the production process. Let's consider a pharmaceutical manufacturing process with network-level separation between the IT and OT networks and integration between the manufacturing execution system and ERP. After profiling the company on professional networking sites, the adversary selects his target, an engineer with access to the OT network. A waterhole attack is set up by responding to one of the engineer's posts on an industry forum. As the engineer is working from home, his home network does not have all the protections of the corporate network. The attack succeeds without any alerts, compromising the engineer's laptop. The attacker shifts into the OT environment when the engineer next connects to the OT network over VPN. Once inside, the attacker performs reconnaissance activities to determine the lay of the land. He finds a data historian system running a dated and unpatched operating system, as well as a network-attached storage device on the OT network that is used to store backups of ladder logic, HMI screens, and historian data. The attacker compromises and pivots to the data historian system on the OT network, establishing persistence in the environment. The attacker is using command and control tunneled through DNS, a byproduct of the MES ERP integration. However, back channels can also be established using USB, acoustic, RF, ultrasonic, electrical, optical, and other air-gap jumping techniques. The information pilfered from the backup storage device is exfiltrated over the command and control channel. Knowledge matter experts engaged by the adversary analyze the exfiltrated data and devise a process-level attack. The attacker finally launches the attack by uploading tainted code to the PLCs controlling the production process, using the data historian as a springboard. The production line has been compromised. If the attack is pulled off by also targeting quality control systems or making subtle changes undetectable by quality control processes, an inferior product will be produced and delivered to market, damaging the long-term brand value of the drug. The competitor has achieved his objective. Now, let's see the situation where operations are monitored in the Security Operations Center using Splice. Splice would recognize the attempted attack at a number of stages. When the compromised engineering system is connected to the OT network via VPN, behavioral profiling immediately picks up reconnaissance activity. The exploit used in the lateral attack against the data historian triggers as an indicator of compromise. Even though DNS queries used to tunnel the command and control sessions are a normal behavior expected to be seen coming from the data historian, anomaly detection would identify the unusual pattern as an outlier. Uploading ladder logic from the data historian would trigger as a newly seen behavior. Early stage detections allow for disrupting the kill chain before further damage can be done. The agent follows the SOC workflow to escalate and alert the client's engineering support manager. Splice provides the audit trail and behavioral profile to confirm suspect behavior, and the client quarantines the offending system for forensic investigation. Severe damage to the brand and production processes are avoided. Observed node behavior, activity at the infrastructure level, detections, investigations, and prevented attacks are shared with the response team. A forensic investigation traces the control breakdown back to the engineering workstation, waterhole attack, and inadequate work from home protection. Control improvements are made to prevent this from happening again. Besides detecting attacks, Splice also has the capability to change the risk profile of OT networks, enabling vulnerable components to continue in operation. This can be achieved by migrating to edge and in-path modes, where an encrypted and protected overlay network replaces inadequate isolation and air gaps. Deployed in these modes, Splice actively prevents cyber-physical attacks and enables operational technology in distributed geographical areas, such as critical infrastructure, healthcare, smart city sensor networks, transportation networks, mining, and multi-stage manufacturing, to operate securely across hostile carrier and enterprise infrastructure networks with lower trust levels. Splice, the logical alternative to air gaps and firewalls.